The biggest lie science ever told you. You have been lied to. Not maliciously, not deliberately, but thoroughly, and from a very young age, and with pictures. Beautiful pictures. A tiny, impossibly dense point of something we never quite say what, and then, boom, an explosion. Fire and light and matter flying outward in all directions, like a grenade going off in a dark room, debris screaming away from a central point, the universe expanding like a shrapnel cloud from some cosmic weapon. That is the picture in your head. I know it is, because it's in everyone's head. It's in textbooks, it's in documentaries, it's in the mouths of people who should know better, and it is wrong. Not a little wrong, not wrong in the details. Fundamentally, categorically, embarrassingly wrong in a way that changes everything about how you understand where you came from and what the universe actually is. There was no explosion, there was no center, there was no point that things flew outward from, there was no outward, there was no from. What actually happened is stranger, more beautiful, more mind-dissolving than any explosion. And nobody told you, I'm going to fix that right now. What you think happened and why you're wrong. Let me start by asking you to do something uncomfortable. I want you to take the picture in your head, the explosion picture, the fireball picture, the boom picture, and I want you to set it aside. Not throw it away, just put it down. We'll come back to it, and we'll explain why it's wrong, piece by piece. And by the time we're done, you'll understand not just why it's wrong, but why the wrong picture is so seductive, so persistent, and so genuinely difficult to replace with the true one. Because here's the problem. The true picture is harder. It requires something that human beings are genuinely bad at, which is thinking about space itself as a thing that can change. Not things moving through space. Space, the fabric, the container, the stuff in which things happen. We are very good at thinking about objects moving. Throw a ball. It moves through air, through the space of the room, and lands somewhere. Our brains are spectacularly calibrated for this kind of motion. Evolution spent a long time making sure our ancestors could track a thrown spear, estimate the arc of a falling branch, judge the speed of a running predator. We are motion tracking machines of extraordinary sophistication. But the universe, it turns out, does not care about our evolutionary history. The universe is not obligated to behave in ways that are easy for savanna-adapted primate brains to visualize. And the Big Bang is perhaps the single clearest example of nature doing something that is genuinely, deeply, structurally difficult for us to picture. So let me try to build the true picture carefully, step by step, starting from what we actually mean when we say the Big Bang. The insult that became a theory, the phrase Big Bang, was actually invented as an insult. In the late 1940s and early 1950s, there was a genuine scientific debate about the origin of the universe. One camp believed the universe had no origin, that it existed in a steady state, matter being continuously created to fill the gaps as the universe expanded, the universe looking more or less the same at all times and in all places. The other camp believed the universe had a definite beginning, a moment of extreme density from which everything evolved. The astronomer Fred Hoyle, who was firmly in the steady state camp, was on a BBC radio program in 1949 and wanted to characterize the opposition's view in a way that would make it sound ridiculous. He said something like, and I'm paraphrasing, "They believe the universe began with a Big Bang." He meant it mockingly. He meant, isn't that a silly, unscientific, cartoonish idea? The name stuck. And with the name came the image. A bang, an explosion, boom. And this is the first thing I want you to understand. The scientists who actually developed the Big Bang theory, George Lemaitre, George Gamow, Ralph Alpher, Robert Herman, none of them thought of it as an explosion. Lemaitre, who first proposed the idea in 1927, called it the hypothesis of the primeval atom or the cosmic egg. He wasn't thinking about explosions. He was thinking about the mathematics of general relativity and what those equations told him about the early universe, and those equations said nothing about an explosion. The explosion picture came from the name. The name came from a sneer, and the sneer has been confusing people ever since. What really happened, so what did happen? Let me give you the first piece of the true picture, and I want you to hold it carefully, because it's the piece that everything else rests on. The universe is expanding, not things in the universe are flying apart. The universe itself, the space, the fabric, the coordinate system in which all matter exists is expanding, growing, getting bigger. Now, this sounds like I might be saying the same thing in different words. I am not. The distinction is absolutely critical, and I'm going to use an analogy that's imperfect but useful. Imagine you take a rubber balloon and you paint dots on it, little dots scattered all over the surface. Now inflate the balloon. What happens to the dots? They move apart from each other. Every dot moves away from every other dot. But here's the crucial question. Which dot is at the center of the expansion? None of them. No dot is special. No dot is the origin point from which the others flew outward. Every dot sees every other dot moving away from it. And every dot could equally well say, I am stationary, and everything is moving away from me. The expansion has no center. The expansion is a property of the surface itself, not a motion of the dots through some pre-existing space. This is what the universe is doing, and it's been doing it since the very beginning. Now, you might say, well, but the balloon analogy isn't perfect, because the balloon has an inside and an outside, and the balloon's surface is expanding into the surrounding space of the room. The universe doesn't have a surrounding space it's expanding into. The universe is everything. There is no outside. You're absolutely right. The analogy is imperfect. The balloon is a two-dimensional surface, expanding in three-dimensional space. The universe is a three-dimensional space, and it's not expanding into some higher dimensional space, or if it is, that higher dimensional space has no observable consequence for us, and we can't say anything meaningful about it. For all practical purposes, the universe is expanding, and there's nothing outside it. And the expansion is just a fact about the geometry of space itself. I told you this was hard to picture. Now, here's where the Big Bang comes from. Ready? If the universe is currently expanding, if all the galaxies are currently moving apart from each other, then go backwards in time. Run the movie in reverse. The galaxies get closer. The space between them shrinks. Go back far enough, and everything is very close together. Go back even further, and everything is extremely close together, and the density and temperature are enormous. Go back to the very beginning, and everything, all the matter and energy in the observable universe was compressed into an extraordinarily hot, extraordinarily dense state. That state is what we call the Big Bang, not an explosion, a state, an initial condition. The universe began in a state of extraordinary density and temperature, and has been expanding, cooling, thinning out, forming structure ever since. There was no explosion because there was nothing to explode into. There was no outward because all of space was the hot, dense stuff. There was no external space for things to explode into. There was no center because the hot, dense state was everywhere. It wasn't a point in space. It was all of space in a very compressed form. And this is where the picture you have in your head goes most catastrophically wrong. The picture in your head has the Big Bang happening at a point, a tiny point in otherwise empty space, and matter flying outward from that point into the emptiness. But there was no emptiness. There was no surrounding void. There was no point. There was just space, very hot, very dense, everywhere, and it expanded. The Big Bang didn't happen at a location. It happened everywhere simultaneously. And if you find that sentence difficult to hold in your mind, good. That's what honest physics feels like sometimes. Space itself is the thing. That's expanding. I want to go deeper into this idea of expanding space, because I think most people, even after hearing the balloon analogy, still secretly think of expansion as motion. As stuff moving through space, the way a gas expands when you heat it, molecules bouncing around and filling a larger volume. That's not what's happening. And the difference matters enormously. When a gas expands, when you heat a balloon of gas and it gets bigger, the molecules are moving. They're moving through space. The space itself isn't changing. If you could somehow stop all the molecules in place, the space would be exactly the same as it was before. Space is the passive stage on which molecular motion happens. When the universe expands, space itself is changing. The geometry is changing. The distances between points in space are changing, not because anything is moving through space, but because the space is, in some sense, being stretched. Let me give you a way to see why this distinction matters observationally. If the expansion of the universe were like a gas expanding things flying through space, you would expect a Doppler shift in the light you receive from distant galaxies. And you do observe a redshift. Galaxies are redshifted. Their light is stretched to longer, redder wavelengths. The question is, what is causing the redshift? For nearby galaxies, nearby in cosmological terms, the expansion is slow enough that you can think of it approximately as recession velocity, as motion through space, and the Doppler formula works well enough. But for very distant galaxies, the picture breaks down. Some distant galaxies appear to be receding from us faster than light. And you might say, that's impossible. Nothing moves faster than light. And you'd be right if we were talking about motion through space. Nothing moves through space faster than light. That's special relativity, and it's correct. But space itself can expand at any rate. There's no speed limit on the expansion of space. Galaxies aren't moving faster than light. The space between us and them is expanding faster than light. Nothing is violating relativity. Light is still moving at the same speed through local space. It's just that the space is expanding so fast that the light, even at its maximum speed, is losing ground. Hubble's discovery and the proof of no center. Let me tell you about the redshift more carefully, because it's one of the greatest stories in the history of science, and most accounts of it get the physics slightly wrong in a way that feeds the explosion picture. In 1929, Edwin Hubble published one of the most consequential papers in scientific history. He had been systematically measuring the distances to galaxies using Cepheid variable stars as standard candles, objects whose true brightness he could calculate, and therefore whose distance he could infer from their apparent brightness, and comparing those distances to the measured redshifts of those galaxies. What he found was a relationship. The farther away a galaxy was, the faster it appeared to be receding. Not randomly scattered velocities, not a few moving toward us and most moving away, but a systematic linear relationship. Double the distance, double the recession speed. Quadruple the distance, quadruple the recession speed. This relationship is now called the Hubble law, and it has a very specific signature that distinguishes an expanding universe from an explosion. Think about what an explosion looks like. You have a center, the point of the explosion, and material flying outward from that center in all directions. The fastest material is farthest away because it's had time to travel. Slower material is closer to the center. From any given point, you would see the fastest things farthest away and the slowest things closest. Yes, that's consistent with Hubble's observation, but here's the key. From any given point that isn't the center, you would see a clear directionality. Things would be moving faster away from the explosion center than toward it. The expansion would not look the same in all directions. But in our universe, Hubble's law is the same in every direction. No matter which way we look, the relationship between distance and recession speed is the same. There is no preferred direction. There is no direction where things are moving faster, no direction where they're moving slower, no indication of a distant point from which everything originated. This is exactly what you'd expect if space itself is expanding uniformly. And it is completely inconsistent with an explosion at a single point. There's another way to see this that I find even more striking. Consider how you would look as an observer if you were standing at an arbitrary galaxy, not the Milky Way, just some random galaxy in the universe. From your galaxy, you would see all other galaxies moving away from you. Nearby galaxies moving away slowly, distant galaxies moving away faster, in accordance with Hubble's law. You would be forgiven for thinking you were at the center of the universe, with everything fleeing from you specifically. Now move to a different galaxy, a galaxy that, from our perspective here in the Milky Way, appears to be racing away from us at high speed. From that galaxy, what do you see? You see all other galaxies moving away from you, nearby ones slowly, distant ones fast. In accordance with Hubble's law, you appear to be at the center of the universe too. Every galaxy in the universe appears to be at the center of the expansion, which means no galaxy is the center. The expansion has no center. There is no special point from which everything originated and flew outward. This should bother you. I want it to bother you, because it deeply bothered the physicists who first figured it out. We are very attached to the idea that things have centers, that processes have origins, that you can point to a place and say, it started here. The universe is telling us with extraordinary clarity that the Big Bang was not like that. It had no here. It happened everywhere. Let me also address something that I know is rattling around in the back of some of your heads. But wait, you're thinking, if we run the expansion backward, don't all the galaxies converge on a single point? Doesn't that mean there is a center back in the past? This is a subtle point, and it requires careful thought. Yes, in the naive picture, if you run everything back, the galaxies converge. But what converges is not matter in pre-existing space converging to a point. What happens is, as you go back in time, the space itself becomes smaller. All of space, the whole universe, shrinks. The space doesn't converge to a point in some larger pre-existing space. The space just gets smaller. And at the moment we call the Big Bang, the observable universe was extraordinarily small, possibly of zero size, in the idealized mathematical limit. But there's no point in a pre-existing void. There's no center in a larger surrounding space. There is only space itself and its evolution over time. Before the Bang, what was actually there? Now, I want to ask a question that makes cosmologists shift uncomfortably in their chairs. What was there before the Big Bang? And I want to start my answer with complete honesty. We don't know. We have ideas. We have speculations. We have mathematical frameworks that may or may not correspond to reality. But we do not know what, if anything, preceded the Big Bang. And I think it's important to say this clearly before doing anything else, because the honest answer is far more interesting than a false confident one. But here's what makes the question even more interesting and difficult than it first appears. The question, what was there before the Big Bang, assumes that before is a meaningful concept at that boundary. It assumes time existed before the Big Bang, stretching back into the past, waiting for the universe to appear in it. And that assumption may be wrong. Time, according to general relativity, is not a background fixed structure that the universe exists within. Time is part of the universe. It's woven together with space into a four-dimensional fabric called space-time. And this fabric has a physical reality. It can curve, it can bend, it can have a geometry. Gravity, according to Einstein, is the curvature of this space-time fabric. The presence of mass bends space-time, and that bending is what we experience as gravitational attraction. If time is part of the universe, part of the physical structure of things, then asking what happened before the Big Bang is a little like asking what is north of the North Pole. It's not a question that has an answer because it's using the concept before in a context where before doesn't apply. This is not a dodge. This is not me changing the subject to avoid a hard question. This is a genuine, important, potentially correct observation about the structure of reality. And it has a fascinating history. Hawking, Hartle, and the no-boundary proposal. Stephen Hawking and James Hartle developed a proposal in the 1980s called the no-boundary proposal, or the Hartle-Hawking state. It's a mathematical framework for thinking about the origin of the universe using quantum mechanics and general relativity, and it reaches exactly this conclusion. Time itself has a boundary at the Big Bang, and asking about before is not a meaningful question. Hawking had a wonderful way of explaining it. He would say, asking what happened before the Big Bang is like asking what is south of the South Pole. You can stand at the South Pole and walk in any direction, and you'll be heading north. There is no south from the South Pole. Time, in the no-boundary proposal, has a similar character at the Big Bang. You can go back to the very earliest moments, but there is no earlier than the beginning. The beginning is a boundary of time, not a moment within time. Now, I want to be careful here. The Hartle-Hawking proposal is a theoretical framework, not an established fact. It's a beautiful piece of mathematics, and it may or may not describe reality. We cannot currently test it directly. But it illustrates the important point that the question, before the Big Bang, may simply be malformed, may be asking something that doesn't have a meaningful answer because of the nature of time itself. There are other proposals. In eternal inflation models, which I'll talk about later, the Big Bang that produced our universe may have been a local event in a much larger structure, a bubble of expansion in an eternal inflating background. In cyclic models, the Big Bang was a collision between membranes in a higher dimensional space, and before the Big Bang is a previous cycle. In loop quantum cosmology, the quantum nature of space-time prevents the density from becoming truly infinite, and the Big Bang was preceded by a collapsing phase, a big crunch of a previous universe that bounced. All of these are speculative. All of them are taken seriously by at least some physicists. None of them have been confirmed by observation. What they share is the recognition that the Big Bang is not simply the beginning of matter in a pre-existing infinite space. The Big Bang is the beginning, or near the beginning, or a transition point of space and time themselves. It is not an event that happens somewhere. It is not even precisely an event that happened at a particular time. It is a boundary of the very coordinate system we use to describe events. The singularity is your ignorance, not a physical object. I also need to talk to you about the singularity, because I think it's one of the most misunderstood concepts in all of popular science. When physicists use the equations of general relativity to trace the expansion of the universe backward, following the expansion back toward its origin, the density and temperature climb without bound. As we approach the moment of the Big Bang, the density approaches infinity, the temperature approaches infinity, the curvature of space-time approaches infinity. This mathematical result, infinity, is called a singularity. And here is what I want you to understand about singularities in physics. They are not physical objects. They are not real things that exist. A singularity is a signal that your equations have broken down, that the mathematical model you're using is being pushed beyond its domain of applicability, and the result, infinity, is the model's way of saying, I don't know what's going on here. This is not unusual in physics. It happens all the time. Newtonian gravity predicts infinite force between two-point masses as their separation goes to zero. This doesn't mean infinite forces exist. It means Newtonian gravity isn't the right theory at that scale. Classical electrodynamics predicts infinite energy for a point electron. This doesn't mean electrons have infinite energy. It means classical electrodynamics needs to be replaced by quantum electrodynamics at small scales. Similarly, the singularity at the Big Bang is not telling us that the universe began as an infinitely dense point. It's telling us that general relativity, extrapolated all the way back to the beginning, eventually breaks down at very early times, at times less than about 10 to the power of minus 43 seconds, called the Planck time. Quantum effects on gravity become important, and general relativity is no longer adequate to describe what's happening. We do not have a working theory of quantum gravity. We don't know what happened in that first tiny fraction of a second. The singularity is our ignorance, not a description of a physical state. The honest answer to what was there at the very beginning is we don't know, and our current best theories break down before they can answer the question. This is uncomfortable, and I think it's right, and I think pretending otherwise does everyone a disservice. The evidence that proves all of this, let me shift from the theoretical to the observational, because I think it's important to be clear about why we believe all of this. What is the actual evidence for the Big Bang model? Not the explosion picture, the real model, the hot, dense, everywhere expanding space picture. The evidence is extraordinary. It comes from multiple, completely independent directions, and it all converges on the same picture with remarkable consistency. Let me take you through the major pillars. The first and most basic is the one we've already discussed. Hubble's observation of the expansion. The universe is expanding. Every galaxy we can see is redshifted. Its light is stretched by an amount that increases linearly with distance. This is exactly what you expect from a uniformly expanding space. It is the foundational observation of modern cosmology. But expansion alone doesn't prove there was a hot, dense beginning. You could imagine a universe that has always been expanding at the same rate forever, with matter continuously appearing to fill the gaps, the steady state model I mentioned earlier. So what rules that out? The cosmic microwave background, the afterglow of creation. The second major pillar is the cosmic microwave background radiation, which I love with an almost embarrassing fervor. This is, to my mind, one of the most beautiful and direct pieces of evidence in all of science. In a hot, dense, early universe, billions of degrees hot, far too hot for atoms to exist, matter and light are in equilibrium. Light can't travel freely. Every photon is immediately absorbed and re-emitted. The universe is opaque, like the inside of a very hot star. As the universe expands and cools, eventually, about 380,000 years after the Big Bang, the temperature drops enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the universe becomes transparent. The light that was everywhere, trapped in the hot plasma, is released. It streams freely in all directions. That light, now cooled by the expansion of the universe to a temperature of just 2.7 degrees above absolute zero, is still streaming through the universe today. It fills space uniformly in every direction. We call it the cosmic microwave background radiation, and we can detect it. In 1964, Arno Penzias and Robert Wilson, two radio engineers at Bell Labs, detected an annoying, persistent, uniform noise in their antenna that they couldn't eliminate. They tried everything. They removed bird nests from the antenna. They cleaned off what Penzias charitably described as white dielectric material. The noise remained. It was uniform in all directions. It had the characteristic spectrum of a thermal source at about 3 degrees Kelvin. They had, without meaning to, detected the afterglow of the Big Bang. The cosmic microwave background is not just a warm glow. It has structured tiny temperature fluctuations, 1 part in 100,000, that encode the state of the universe at 380,000 years old. These fluctuations are the seeds of all the structure we see today, the galaxies, the galaxy clusters, the cosmic web. They were measured with extraordinary precision by the COBE, WMAP, and Planck satellites, and they match the predictions of the Big Bang model to a degree that should make your jaw drop, not just qualitatively, quantitatively. The angular pattern of the fluctuations, the relative amplitudes at different scales, the statistical properties, all of it matches the theoretical prediction to the precision of the measurements, which in some cases is better than 1%. This is not the kind of agreement you get from a wrong theory. This is the kind of agreement you get from a theory that is capturing something deep and real about the universe. The steady-state model has no equivalent prediction for the cosmic microwave background. There's no reason in the steady-state model why the universe should be bathed in a uniform thermal radiation. The observation of the CMB essentially ended the debate between the Big Bang and steady-state models. The steady-state model is gone, not discredited by opinion or authority, but killed by data. Big Bang nucleosynthesis, where your hydrogen came from. The third major pillar is Big Bang nucleosynthesis, the prediction of the abundances of the light elements. In the very early universe, when the temperature was billions of degrees, nuclear reactions could occur. Protons and neutrons were combining and falling apart, but as the universe expanded and cooled through a narrow temperature window, roughly 1 second to 3 minutes after the Big Bang, the conditions were right for stable light nuclei to form. Not just hydrogen, but deuterium, heavy hydrogen, helium, 3, helium, 4, and lithium, 7. George Gamow, Ralph Alpher, and Robert Herman worked out the theory of Big Bang nucleosynthesis in the 1940s. They calculated, given the conditions we believe existed in the early universe, what fraction of the matter should end up as hydrogen, as helium, as deuterium. Their prediction, about 75% hydrogen, about 25% helium by mass. Everything else, all the carbon, oxygen, nitrogen, iron, gold, everything is made in stars, not in the Big Bang. The Big Bang only makes the lightest elements. What do we observe? When we look at the oldest stars, the least chemically evolved regions of the universe, the regions that haven't been processed through many generations of stars, we find about 75% hydrogen, about 25% helium. The prediction and the observation are in extraordinary agreement. The Big Bang nucleosynthesis calculation also constrains the density of ordinary matter in the universe, the amount of protons and neutrons. And that constraint is consistent with, and indeed predicted, the existence of dark matter before the other evidence for dark matter was understood. The nucleosynthesis calculation says there's only enough ordinary matter to explain about 5% of the energy content of the universe. The rest has to be something else. The Big Bang model is not a single piece of evidence. It is a tight web of interconnected predictions and observations, each independent of the others, all consistent with each other, all pointing to the same picture of an early, hot, dense, expanding universe. Inflation, the real story of the first instant. Now I want to tell you about something that modifies the simple Big Bang picture in a profound way. Something that was discovered, or rather, theoretically proposed, to solve some deep puzzles that the basic Big Bang model left unsolved. I'm talking about inflation, cosmic inflation. The hypothesis that in the first fraction of a second after the Big Bang, in a time interval so short it makes your head spin, something like 10 to the minus 36 seconds, the universe underwent a period of extraordinarily rapid exponential expansion. Not the gentle expansion we see today, but expansion so violent that the universe grew by a factor of at least 10 to the power of 26, 100 trillion in a tiny fraction of a second. This idea was proposed by Alan Guth in 1980, and it was motivated not by a desire to make the universe more complicated, but by a need to explain 3 specific puzzles that the basic Big Bang model couldn't answer. Puzzle 1, the flatness problem. General relativity allows for space to have different geometries. Space can be positively curved, like the surface of a sphere in such a universe. If you travel far enough in any direction, you come back to where you started, and parallel lines eventually converge. Space can be negatively curved. Like a saddle in such a universe, parallel lines diverge. Or space can be flat, Euclidean, the geometry you learned in school, where parallel lines stay parallel. Observations tell us that our universe is flat, or very nearly so. The geometry of space on large scales is indistinguishable from flat. The problem is that a flat universe is an extremely unstable configuration in general relativity. If the universe starts with even a tiny deviation from perfect flatness, that deviation grows over time. A universe that's even slightly curved at the Big Bang becomes wildly curved very quickly. For the universe to be as flat as we observe it today, after 13.8 billion years, it must have been extraordinarily flat at the beginning, flat to one part in 10 to the 60th power. Why would the universe start off so perfectly flat? The basic Big Bang model has no answer. It just has to be a coincidence, a fine-tuning, an uncomfortably precise initial condition. Inflation solves this. If the universe underwent a period of rapid exponential expansion, any initial curvature gets ironed out. Think of inflating a balloon, initially wrinkled and curved, but as it inflates, the surface becomes flatter and flatter, and any local region becomes increasingly flat. Inflation does the same thing to the curvature of space. Whatever the initial geometry was, inflation drives it to flat. Puzzle 2, the horizon problem. Look at the cosmic microwave background radiation. It's uniform, the same temperature in every direction, to 1 part in 100,000. This uniformity is extraordinary. It means that regions of the early universe that were on opposite sides of the observable universe, regions that, in the basic Big Bang model, could never have been in contact with each other because light wouldn't have had time to travel between them, somehow ended up at exactly the same temperature. How? In the basic Big Bang model, this is deeply puzzling. If two regions of the universe have never been able to communicate, never exchanged energy, never reached thermal equilibrium, why are they the same temperature? The standard Big Bang model has no good answer. It just says they happen to start at the same temperature. Another coincidence, another fine-tuning. Inflation solves this too. If there was a period of inflation, then the entire observable universe we see today, all of it, including the regions that seem causally disconnected, originated from a tiny patch of space that was well within causal contact before inflation. Everything we can see was once close enough together to thermalize to reach the same temperature. Then inflation expanded that tiny patch into the enormous universe we observe, stretching it so much that different parts of the sky appear causally disconnected in the basic Big Bang picture. In the inflationary picture, the uniformity of the CMB is not a coincidence. It's a consequence, quantum noise that became galaxies. But here's where it gets even more extraordinary. Inflation doesn't just solve the flatness problem and the horizon problem and the monopole problem. It makes a specific, testable prediction about the structure of the universe that we can check. During inflation, the universe was so small that quantum mechanical fluctuations were important. The quantum uncertainty principle, the fundamental fuzziness of nature at small scales, meant that the density of the inflating universe was not perfectly uniform. There were tiny random fluctuations in density from point to point. Inflation took those quantum fluctuations and stretched them. The expansion magnified those tiny density variations from quantum scales smaller than atoms to macroscopic astrophysical scales. And those density variations, frozen into the structure of space, became the seeds for all the structure we see in the universe. The slightly denser regions eventually became galaxies. The slightly less dense regions became the voids between galaxies. The universe we live in, with all its galaxies and clusters and filaments and voids, grew from quantum noise. This is one of the most audacious predictions in the history of science. And when we look at the pattern of the cosmic microwave background, those tiny temperature fluctuations I mentioned, the pattern matches the prediction of inflation extraordinarily well. The statistical distribution of the fluctuations, the relative sizes of the peaks in the power spectrum, it all matches. Now, inflation is not proven. It is a theoretical framework, and there are various versions of it. And some aspects are difficult to test, but it is the leading paradigm for understanding the very early universe, and the evidence in its favor is substantial. There was no explosion. What really happened? I've taken you through a lot of physics. Let me now take you back to the title of what we're discussing and say it clearly one more time. There was no explosion in the Big Bang. I want you to understand, now that we've gone through all of this, exactly how many different ways that statement is true. There was no explosion because there was nothing to explode into. There was no pre-existing empty space surrounding a dense ball of matter. There was only space itself, and it expanded. There was no explosion because there was no center. An explosion has a center, a point of origin from which the shrapnel flies outward. The Big Bang has no center. It happened everywhere. Every point in space was part of the Big Bang, and no point is more the origin than any other. There was no explosion because there was no outward. Outward implies a direction away from the center into surrounding empty space. In the Big Bang, there was no surrounding empty space. There was no outward direction. Space itself was expanding in all directions simultaneously, and those directions don't point outward from anything. There was no explosion because the expansion isn't caused by an initial bang, an impulse, a push. The expansion is driven by the energy content of the universe, by the radiation and matter filling space, and in our current era, by the mysterious dark energy that seems to be accelerating the expansion. It's not the residual momentum of an explosion. It's an ongoing dynamic process determined by the content of the universe. And there was no explosion in the sense that the word explosion implies violence, disorder, destruction. The Big Bang was instead extraordinarily structured. It produced, from what appears to be an incredibly simple initial state, an extraordinarily complex universe, one with galaxies, stars, planets, life, and beings capable of asking questions about their own origin. You are made of Big Bang hydrogen. Let me talk about what this means for you, specifically, for your place in the universe, for the question of where you came from. If the Big Bang were an explosion at a center, then there would be a center of the universe. Depending on how far we are from that center, we might be in a special place or an ordinary place, but there would be a center, and our location would be measurable relative to it. The universe has no center, or which amounts to the same thing, every point is equally the center. You are, right now, at the center of the observable universe. So is every other observer at every other location. The universe has no edge, no special place, no origin point that is more there than anywhere else. This is either deeply comforting or deeply unsettling, depending on your temperament. Now, let me tell you something about what you're made of and how it connects to all of this. Every atom in your body heavier than lithium was made in a star. The carbon in your DNA, the oxygen in your lungs, the calcium in your bones, the iron in your blood, none of it was made in the Big Bang. The Big Bang made only hydrogen, helium, and a tiny bit of lithium. Everything else, every single heavier element that constitutes the chemistry of life, was forged in the nuclear furnaces of massive stars and scattered into space when those stars exploded as supernovae. So you are made of star stuff, as Carl Sagan was fond of saying. But the hydrogen in you, the hydrogen in every molecule of water in your body, the hydrogen in every organic molecule in every cell that hydrogen was made in the Big Bang 13.8 billion years ago, in the first 3 minutes of the universe, the hydrogen in you is almost as old as the universe. Let that sink in. You carry atoms that have existed for almost the entire 13.8 billion year history of the cosmos. And the space through which those atoms have traveled, the space that those atoms are currently occupying, the space that constitutes the universe in which your existence is possible, that space expanded from a hot, dense, everywhere at once beginning. Not an explosion, not the bang, a cosmic stretching, a universal expansion, an evolution of space and time from a primordial state to the vast, mostly empty, but wonderfully structured universe we find ourselves in today. Does the universe have an edge? I want to address one more thing before I'm done, because I think it's a question that nags at thoughtful people who've been following all of this. If the universe has no center, if every point is equivalent, if the Big Bang happened everywhere, does the universe have an edge? The universe might be infinite. If it's infinite, then obviously it has no edge. An infinite universe with no special points and no boundaries. The Big Bang happened everywhere in an infinite space, and that infinite space has been expanding, growing from one infinite size to a larger infinite size, which is something that mathematics allows, even if it strains intuition. Or the universe might be finite, but without a boundary like the surface of a sphere, which is finite in area but has no edge, no boundary, no point where it ends. In a positively curved universe, space might close back on itself, so that traveling far enough in any direction brings you back to where you started. There would be no edge because the space is closed. Either way, infinite and flat, or finite and closed, there is no edge. There is no boundary where the universe ends and something else begins. The universe is everything, by definition. Now I know some of you are thinking, but if the universe is expanding, expanding into what? When we say the universe is expanding, we don't mean it's getting bigger in some larger space. We mean the distances within the universe are increasing. The fabric of space is stretching. The metric, the mathematical object that tells you how to measure distances is changing. 2 points that are currently a meter apart will be, in the future, slightly more than a meter apart. Not because they moved, because the space between them stretched. There is no outside the universe for it to expand into. The expansion is a statement about the internal geometry of the universe, not about its size relative to some external reference. I find this thought difficult. I suspect you do too. I think it's important to sit with that difficulty rather than resolving it with a false picture. The discomfort you feel is the correct response to a genuinely strange fact about the universe. The universe doesn't owe us intuitiveness. The beautiful, uncomfortable truth. I want to end with what I think is the deepest lesson in all of this. The Big Bang is one of the most extraordinary things we have ever figured out about the universe. It is extraordinary, not because it's an explosion, it isn't, but because it tells us that the universe has a history, a deep, long, directional history, a past that was radically different from the present, a state 13.8 billion years ago that was hot and dense and simple, out of which all the complexity we observe, galaxies, stars, planets, chemistry, biology, consciousness has evolved. And we know this. We know it with evidence, with measurements, with precision, with theoretical understanding of why it had to be this way. Not with certainty. There are things at the edges of our understanding, the very beginning, the question of what came before, that remain genuinely open. But the broad outline, the fact of cosmic expansion from a hot, dense beginning, is about as well established as anything in science. This is a triumph of human curiosity. A species that evolved to track prey on the African savanna using brains that were selected for social interaction and short-range problem-solving has figured out the history of the universe, has looked at the faint glow of radiation from 380,000 years after the beginning of time and extracted from it precise information about the composition and geometry of the cosmos, has built a coherent, consistent, mathematically precise picture of 13.8 billion years of cosmic history. That is not nothing. That is, in my view, one of the most remarkable things that has ever happened. And the lesson I want to leave you with is this. Be suspicious of simple pictures. Be suspicious of the fireball, the explosion, the boom. Not because simple pictures are always wrong, sometimes they're useful approximations, but because the universe is under no obligation to be simple, and the places where the simple picture breaks down are often exactly where the most interesting physics is hiding. The Big Bang is not an explosion. It is an expansion of space. It has no center. It happened everywhere. There was no empty void surrounding a ball of matter. There was just space, hot and dense, and it expanded. And here we are, made of hydrogen forged in the first 3 minutes and carbon forged in stars, sitting on a rock, orbiting a star on the outskirts of a galaxy in an expanding universe, wondering where we came from. We figured out where we came from. That's beautiful. And it's more beautiful for being true rather than merely dramatic. There was no explosion. There was something much stranger and much more wonderful. And now you know it.